So time division multiplexing is how the signals of 8086 is divided. Like we have seen clock. Clock of 8086 is made of a bunch of signals TW and T4. So these 5 clocks will form the machine cycle of 8086. So they are T1, T2, T3, T wait and T4. So those 5 clocks are the minimum amount of time for any operation to execute. So those bunches will be either 1 or 2 or 3 for every instruction. So it depends on the weight of the instruction. Maybe it's a no operation. It might take one different machine cycle. If it is an addition, it might end up using 2 machine cycles. Maybe it's a compare, or if it's a jump. It depends on the weight of the operation, the amount of machines. So this becomes a machine. The number of machine cycles it can usually consume. Now, like we discussed, how they are divided. They are divided based on this. Your address works in T1 stage and your data works from T2 to T4. That is how it gets divided. So whenever the data comes out, it's a parallel distribution. So either way it can go. Now what we have to do is we have to channelize the data based on the time. So to allow the data in and out, we are connecting few pieces of hardware. So here we connect something called a latch, and here we connect something called as a buffer or a transceiver. So what will a latch do? Latch will allow the address bus, whereas buffer will allow the data bus. When should the latch work? Now the question is, when should the latch work? Latch should work whenever we want the address to come out. Whenever we want the address to come out is T1. So this is where the latch will work, and rest of the time it is off. Same is with the data. The data bus will work during T2 to T4. Rest of the time it should stay off, and that is how you synchronize the data. So at the same time address and data are coming out, but the latch is on during T1, the buffer is on during T2 to T4. So there should be a signal which will switch on and off them. That is called as ALE, which is called as address latch enable. Similarly, data is enabled by DEN bar. Data enable. So address latch enable and data enable are a couple of important signals. So ALE and DEN. So ALE is 1 when it is 1, when it is 0. Address latch should be 1 whenever we want the address to go out. When do we want the address to go out? During T1 cycle. So during T1 it is on, during T2 to T4 it is off. When is data enable working? During T1, sorry, this is a DEN bar. So DEN is enabled during T2 to T4, it is disabled during T1. So as it is DEN bar, it is 1 during T1, 0 during T2 to T4. That is how you will understand the signals. Now address is a unidirectional, whereas data is bidirectional. So to control the flow of data, we require one more pin. That is DT by R bar. DT by R bar represents data transmit or receive. So 1 is transmit, 0 is receive. So this will control the way your address bus and the data bus are connected to the peripherals. And last is the control bus. So how we'll draw the control bus is how the way of the minimum mode and maximum mode works. Ideally minimum mode is a single processor mode and the maximum mode is a multi-processor mode, which is toggled by an MN by MX pin. So how this is controlled to bring out the bring out the control pins. So we ideally have a read bar and a write bar. So read bar, whenever it is 0, as we discussed, it is reading. Whenever W bar is 0, it is writing. So read and write can happen either on memory or an IO. So how do you figure out whether you want to select a memory or an IO device? That is where a pin called M by IO bar comes in. So whenever M by IO, so if it is 1, it is memory. If it is 0, it is IO. Similarly, RD or WR bar. RD bar. 1 it is not reading, 0 it is reading. So is WR bar. These three in combination will generate signals. Memory read, memory write, IO read and IO write. So these are the 4 signals, the control signals that will come out of 8086 and are connected to these devices. So MR and MW are connected here. IOR and IOW are connected here. So that is how you generate the configuration diagram of 8086. So this diagram looks pretty much simple, and all we have is 3 blocks, and 3 blocks are controlled by 3 different buses, and how every bus operates. So latch is controlled by ALE, buffer is controlled by DEN bar, and the direction of the buffer is controlled by DD by R. And so are the control buses are controlled by read, write and IO. So these will be the minimum mode signals. So this is a minimum mode configuration diagram we have seen. So M by IO is a minimum memory or IO. I interrupt acknowledge, address latch enable. We have one more interesting pin called hold and hold acknowledge. Hold, interrupt and interrupt acknowledge are requesting the CPU time, whereas hold and hold acknowledge are requesting the bus time. Suppose there is a copy paste operation. There is no point of CPU involving there. That is where we have come across a concept of DMA. So whenever you want to transfer the data from one memory to other memory, they just need the bus. That controller just requires the bus. So what it will do is it will request the processor to hold the bus. So it will transfer the bus by giving an acknowledge. So the DMA will finish the job and return back the bus. So these are the minimum mode pins. Coming to the maximum mode pins, the same operations are handled by something else called as S0, S1 and S2. So we have interrupt acknowledge, we have read IO, write IO, read memory and write memory. So all the signals are reiterated by something else called S0, S1 and S2 bar. And lock is where someone can't request a bus. Whenever the bus is busy, I can put a lock on it. Queue status will define the status of the queue. So whether the queue is free or empty or to be flushed out. Similar to hold and hold acknowledge, we have something called request and grant. So hold and hold acknowledge are the bus request pin in minimum mode. Request and grant are the pins in the maximum mode. So this is the minimum mode diagram. So how I can convert it to a maximum mode configuration diagram is just replace these pins with S0, S1 and S2 bar, which will generate memory read, memory write, IO read, IO write, IO advanced write and so on. The whole, if you understand the whole diagrams by a difference, so this is the only difference that a minimum mode and a maximum mode actually comes with. The next important part is drawing the timing diagram out of it. So as we have seen, this is a configuration diagram. The timing diagram is a combination of all these signals that we have discussed. So I'll show you a sample timing diagram. The clock is a common part. We have how many states? We have 5 states. So T1, T2, T3, T4 and T5. Sorry, T1, T2, T3, TW and T4. And then we have a ALE. This is the way you have to understand how to draw a timing diagram. So the timing diagram looks complex when you try to remember it, but it is easier when drawn. So ALE, we have seen ALE is on during T1, off during rest of the cycle. So the simple way of representing is ALE is on and rest of the time it is off. And DEN bar. DEN bar is again on during T1 and off during T2 to T4. So how do you represent it is, so understanding the way the timing works and representing it in the form of a diagram will end up creating your timing diagrams. So there are pretty simple timing diagrams that we have. And there are a lot of combinations of timing diagrams that you may be asked for. So how many combinations? Maybe a minimum mode, a maximum mode, a memory, an IO, a read and a write. So you look, in whatever combination it might be a minimum mode memory read, minimum mode memory write, maximum mode memory read, memory write, IO read, IO write. So maybe we have 10 to 12 different combinations or more, but end of the day, how do you represent the timing diagram is a similar way. So you have a clock, so maybe you can look at this half of the diagram. So we have a clock, we have ALE working during T1, rest of the time it is off, and DEN bar which is on during T1 and off rest of the time, and maybe status pins, address and data. The important part is the address and data. Address lines are working during T1, data lines are working during T2 to T4. If you are able to represent the same in the form of a diagram, that works to be a timing diagram. So maybe I can end up representing like this. So address bus during T1 and data bus during T2 to T4. There is a difference between read and a write. So ideally, when do you have the data is whenever you want to write. So maybe I have to put this duster somewhere. So I have an address and I have a data with me. But if I want to pick the pen from somewhere, I have to go there to get the pin or a pen. So to go there and get the pen, I require some amount of time. So as soon as I generate the address, I won't have the data available for me. So the difference between a read and a write would be, there will be a reserved space and a data. So this is how a read signal looks and this is how a write signal looks. Rest of the timing diagrams are the same. ALE never changes its way of working. DN never changes. Whenever you are reading, it is receiving. Whenever you are writing, it is transmitting. Whenever you are accessing a memory, draw a 1. Whenever you are accessing an IO, it is a 0. Whenever you are reading, you put a 0. Whenever you are writing, again you put a 0 over there. So that ends up drawing a timing diagram for us. So this might be the diagram that we have drawn earlier, which looks pretty much complex now. So this is a timing diagram that we have just discussed now. So a clock, an ALE. So what is the timing diagram that we are trying to draw? Minimum mode, read cycle. So minimum mode, read cycle. ALE never changes. DEN, okay, let us put it here. Clock, ALE never changes, T1 on. DN, T1 on, and rest of the time it is off. Now we are selecting a read cycle. Read cycle, dt by r will be receiving. Receiving means it's a 0. So dt by r is a 0. And m by IO, we are asking a memory. So it didn't mention memory or IO. So just we can skip that. And the important part is the address or data. As it's a read, we immediately don't have the data with us. So you have a reserve plus data. Maybe if it's a write, what is the change I have to do? This data, and instead of read, I'll have a write. So this changes my whole diagram into a write. So instead of dt by r, this will be high. So using a single diagram, we can represent n number of diagrams. So that is how the timing diagram works, and this is how all the pin diagram and the pin related stuff is working. So timing diagram and the timing configuration diagrams are pretty much important and pretty much crucial, and straight away it is pretty much easy to score just because we don't have any theory involved in it, just the diagrams. So just a diagram, drawing the neat diagram will fetch you the whole good set of marks. So I hope you have understood the timing diagram and the pin configuration of 8086. Yeah. So we'll start with the programmer's model of 8086. So far we have covered the architecture and the pin structure of 8086, which will let us know the inner view of the processor. Now the programming model helps us understand how a programmer or a developer can work on this processor. The first part of, there are few components of the programming model, which would be the addressing modes. So addressing modes are the way we access the memory and you get your data. So we have a bunch of addressing modes. Ideally, what an addressing mode does is, when we want to pick a data from a memory or from a register, the number of possible ways that you can access the data are the combinations that we call them as addressing modes. Let us take a simple example in C. So there is a way that I can assign A with 2. There is a way I can assign B with A. Or there is a way I can assign P with a pointer and assign a data directly to P. Or maybe I can assign using a pointer directly. These are, end of the day, all these 4 methods are accessing the data but in a multiple way. So if we are accessing the data and assigning the value directly to a register, we usually call it immediate addressing. If we are assigning through a register to a register, we call it register. And if you are accessing a pointer directly, that means an address directly to bring in the data, we call it direct. And here is where we have stored the address inside a register, inside a variable or a register, and we are accessing the memory through a variable. So this becomes indirect. So essentially these are the 4 addressing modes that we have in 8086, and there are a lot which are extensions of all these things. If we classify them or write a equivalence example of everything, so this will be move AL, 12H. So that is, if you are assigning this, we have an immediate value assigning to a register. The example would be move BL, AL. Here we are interacting between 2 different registers. The direct would be involving move AL, 1, 2, 3, 4. Why 1, 2, 3, 4 is the size of the register, the size of the address happens to be 16 bits. And this is how you get your data. So we'll just work on the details and we'll go into it. Move AL, maybe a register. So here we are addressing the value directly and storing it here. Here we are pointing the address using a register. So this register has a address which will bring the value to AL. Here the contents of AL moves into BL. Here the value 12 directly gets assigned with AL. So these are the addressing modes and the equivalences that we have already seen. So if we go pretty much into detail, or how can I classify them by just looking at a set of instructions? So is it just about move? Can't it be add? Maybe if it is add, it still becomes a indirect addressing mode. So addressing mode is not related to the instruction. It is about how you access your data. That means one operand will be a register, one operand will be a immediate value. And if I write the syntax for a register addressing mode, it will be instruction register, register. Maybe what are the examples of register addressing? Move BL, L, add AX, BX, and more to that. So are indirect. So indirect is, one is a register and other happens to be a memory. And similarly the direct. Whenever you are maybe explaining a bit about addressing modes in detail, you have to couple them with the syntax and an example and write an operation for it. So what happens here? The contents of AX are stored with AX plus BX. So how do we write something like this? Maybe if we are talking about this, what happens? The contents of, what contents will move? 1 byte of data From where? From DS colon 1, 2, 3, 4. Why DS is a big question. When we are talking about an address, we have to give two different addresses. One is the base address and other is the offset. I didn't pretty much give anything about the base address here. So we are just talking about the offset. So if I don't mention anything, the default offset happened to be the data segment. Now you already know how to figure out the physical address out of it. DS into 10 plus offset. So 1 byte of data from DS colon of the base address DS and offset 1234H is moved into AL. That is what summarizes this operation. So in order to explain the way the addressing modes works, there is no point of writing big descriptions about it. Simply we can write a simple example, a syntax and a description about it. So these three will help everyone understand what you are trying to explain about everything. So happens here. So we'll have a quick one example before we move on to the next thing. Let us say move AX comma SI. So obviously this is indirect addressing mode, and what happens in this mode? The destination will tell me the size of the data. So what is the operation? Your operation would be, like I said, we have to write a syntax, example and an operation. So the example happened to be move AX comma SI, and the operation is how much data is getting moved? 2 bytes of data is getting moved. From SI is the address. SI becomes an address here. And what is the base address? I didn't mention anything. So it happens to be DS. It is moved from SI to AX. So this 3 lines of will explain what is happening, or maybe the source to the destination. This will let us understand what you are trying to explain about every addressing mode. So you keep this in mind whenever you try to explain any register. Maybe move AX comma BX. What is this addressing mode? This is register. What data is copied? 2 bytes of data is copied from BX to AX. So what is the default syntaxes? The operand, destination and the source. Now the point is, how do I recognize a set of register from a given bunch of registers? From a bunch of given instructions, how do I find a addressing mode? How do we do that? If at all, how do you classify them is, once we have a brace, they either happen to be a direct or an indirect. So if you have a value inside it, it is direct. If you have a register inside it, it is indirect. Similarly, if you don't have a bracket and a plain value, it is an immediate. And if we have both of them as registers, it is register addressing mode. The important part is classifying by discarding. So once you have a instruction, we have to figure out, okay, we have a number. What it can't be a register because both of them are to be registers. It can't be indirect because both of them are to be registers. Oh, we have a bracket. So it is something about memories. So we have direct and indirect. So our obvious choice will be direct. So if you figure out the way to interpret the instruction by an addressing mode by discarding, it will be pretty much simpler. So these are the addressing modes we have, and we have a lot of addressing modes which are extensions of indirect. So if we have SI and DI, we call them indexed addressing. We have BX and BP, we call them based addressing. We have a BX and an SI, we call it based indexed. We have a displacement value, BX and SI, we call it based indexed, relative based and indexed. So all of them are extensions of the indirect addressing. So whenever, again, maybe I'll we will close with the last example. So 50, SI and BP. What is this addressing mode? It either can't be immediate register, direct or indirect. So we have an index register and a base register and a displacement here. So it's a relative based indexed. So how do I coin the definition, or how do I coin the explanation about it? What is the data getting copied? It is 1 byte of data from, I didn't give anything, so it is DS colon SI plus BP plus 50 is getting stored in here. So this is a pretty much simple explanation that you can have anything about any addressing mode. So I think that is where we can wrap up with the addressing modes part. And then we have assembler directives. Assembler directives are the one which will assist your assembler, which will actually assemble your programs and generate the machine codes to understand. They are something additional to your instructions, but they still help your assembler to predict what you are trying to write. Maybe you know the couple of examples. DB means defined byte. So whatever data comes beside it will be stored in the size of bytes. DW is words. ORG is where you want to originate. You have assume, you have segment, and so on. All these things, what do they do is they assist the assembler to understand what you are trying to do. Maybe I start with something called a data segment. Okay, this programmer is trying to start a segment with a name called data. How do I end a segment? You will end a segment called data ends. You will end a program using end. You will end a procedure using endp. You will end a macro using endm. So these are the directives which will tell that what we are actually trying to do apart from the instruction set. So directives are a separate set which are in addition to our instructions. And next comes the instructions. So this is where we have a big bunch of instructions. So the type of instructions that we have starts with data transfer. What comes under data transfer? The data transfer instructions are where your data transfer operations are involved. Starting with move, you have a push, you have a pop, and lot of them. So you have an LEA. And there are a lot of instructions. What do they try to do is, we are not going to discuss in detail about each and every instruction, given the time or something. Move or push or pop, all these set of instructions actually try to transfer the data from one location to other within the CPU or outside the CPU. So move is a instruction. So how do I explain move? So move happened to be transferring the data from source to destination. So what can be a source and what can be a destination? We'll add up to the examples. So I can have move AL comma 1 2 3 4, move AL comma BL. Move can be interpreted using multiple addressing modes. So now we have understood the relation between the instructions and the addressing modes. Addressing modes are the number of ways we can interpret or call the data, and instructions are the plain functionalities that x86 can do. So combination of these both, we can do multiple number of operations. So push will push onto the stack and decrements the stack pointer. Pop will return from the stack and increments the stack pointer, and so on. Here the important part, for every instruction, the couple of things that we have to mention will be the name, the definition, the syntax, example, and the flags. So listing all these things about each and every instruction will help us know what you are trying to explain about every instruction in detail. Next set of instructions would be arithmetic. By the way, all the data transfer instructions What flags get affected? We have 6 status flags. Only except the parity flag, nothing gets affected. Similarly, in the arithmetic instructions, we have an add. Oh, what is the definition of add? Add adds 2 registers and stores back in the destination. What will be the syntax? So add operand 1, operand 2. What can be operand 1? It can be a direct, it can be an indirect, or it can be a register. So happens to be operand 2. Okay, let us write an example. Add ax, bx. I missed one thing, that's the operation. What is the operation? Ax is added with bx and is stored in ax. Okay, what are the flags getting affected? Carry flag might be affected, auxiliary carry might be affected, parity gets affected, 0 gets affected, overflow gets affected, sign flag also gets affected. So this is the way that we have to interpret and explain about each and every of the instructions. So we have a lot of arithmetic instructions: add, sub, mul, div, sign multiplication, sign division, increment, decrement, and then comes your logical operations. Logical operations involve and, or. They are all the bitwise operations. Usually we'll come across the bitwise operations in logical operations: and, or, not, NAND, and then the important part are the rotate and shift. You might have pretty much had in practice in the lab how we are using the shift and rotate instructions. So shifting and rotating. End of the day, what matters is this set of this order will help us understand each and every instruction. Maybe you want to explain about a shift right. Okay, what is the operation of shift right? Shift right, register, count. So the count will tell how many shifts we want to do. The example would be shift right AL, 4. Okay, what happens? AL is shift right by 4. So every time, one important thing is whenever we make a shift, what happens is it goes to the carry flag. Every shifted bit goes to the carry flag. And then comes the important set of instructions which are control transfer. We have a unconditional and conditional jumps. So jump is where how you transfer the control of your program. The conditional jumps and the unconditional jumps. Unconditional jumps will jump without any condition. So whenever you ask it to do, it will never question us back and it does that. So what kind of things we have? Maybe we have a jump, we have a call, we have a return, and so on. But what are conditional jumps? Conditional jumps are the ones which we have pretty much used in the lab as well. Jump if carry, jump if no carry, jump if 0, jump if no 0. So how are they interpreting all these instructions is they are just depending on the flag registers. In the flag, every flag, what does it do? It will actually tell the status of every operation. So if we do a comparison, the comparison will affect the 0 flag, because comparison is nothing but product of 2 different numbers, and we end up having a 0. So if it is 0, both of them are equal. If it is a non-zero, both of them are not equal. Carry will tell me which is greater or which is lesser. Similarly, we use all these conditions to interpret the operations that we are trying to do to bring out the logic. And yes, we have a big list of all these conditional jumps which are pretty much simple to understand, and we had them in practice as well. And one set of instructions that are to be noted are the string instructions. Similar to the data transfer or compare, we have a bunch of string instructions. One important way to understand all the string instructions would be the source of the string instructions is ds:/si, and the destination is the extra segment : da. So if you have understood, at first we have discussed the default registers, which are the offsets for extra segment is di and data segment is si. So when do they come in when do the defaults are working is they are working in the string instructions. So we don't have any additional operands. Your operations will be as simple as move SB. There won't be any operands. Move SB is move string byte. So from where to where? From DSSI to ESDA. And what happens after that? They just don't copy. How much data gets copied? 1 byte of data gets copied from DS colon SI to ES colon DI, and SI and DI are either incremented or decremented by 1. So who will decide whether I should increment or decrement is the direction flag. If the direction flag is 0, I'll increment. If the direction flag is 1, I'll decrement. So all in all, if I want to move the data or the string in a forward direction, I have to replicate move SB, and it just doesn't copy the data, it actually moves the string in the forward direction. The addresses gets auto incremented. So this happens to be move SB. If you are transferring a byte, it is move SB. If you are transferring a word, it is move SW. So 2 bytes SI and DI are incremented or decremented by 2 is a change in the definition. Move SB, and we have compare SB, and when we want to do, we can scan. So to scanning is nothing but finding. So we do a control F operation on a whole word or something. So what character you want to search in the whole string, so you put it in AL and check it on DI. End of the day, this happens to be the source and this is your destination. So where should I check for my string? Oh, you have to check in the destination. AL loading, this happens to be load, and this happens to be store, and this is again scan. These are the 10 to 12 different instructions that we have in string. And machine transfer instructions will be halt and no operation. These are the things which we have in the instruction set. And in the programming model, we additionally have something called interrupts and procedures and macros. Interrupts, procedures and macros are nothing but your functions and interrupts that you have already known. Whenever maybe I write a program of printf, whenever I call a printf, my program goes somewhere, execute the printf program until I find a return statement and will return back and continue its operation. That usually happens when you call a function. Again, whenever I call a printf, the same thing happens. The program goes there, executes and comes back. This is how ideally a function works. So the bigger challenge is, okay, I called a function and it is going there. I have done the operation and I have encountered a return. Where should I return back? Is the question there. So whenever I come across any function call, what I have to do is I have to store the return address. So whenever you make a call, okay, I have to go there, execute and come back. So whenever you come back, you have to start executing from here. So who points the instruction that is to be executed next is your IP, instruction pointer. The base address is your CS. So whenever I am leaving my location, what I'll do is I'll push my CS, IP and flags onto the stack, go there, go to the new address. How do I get the new address? I need to have a new CS and new IP. I'll figure out a new CS and IP. How do I get a new CS IP? You give it everywhere. You write a jump back. What is this back? This back is a label. Label is nothing but an address. So what is the address we are trying to give here is the CS and IP. It will keep on executing until it finds a return. Whenever it finds a return, again they will pop all these 3 back. And whenever I pop out, I got my old CS and IP stored back, and I will keep on continuing the execution. This is the process of executing a function. The difference between a function and an interrupt is, function is what we call inside a program. Interrupts are what they occur and disturb us. So disturbance in this is whenever we are typing a keyboard. or whenever we are closing a program while we are editing, it interrupts us saying that you want to save the program or not, which is uncalled for. We didn't expect it to come, but it still interrupted the closing part. So interrupts are good and bad in a way you actually see it. But interrupts doesn't happen in the sequence of a program, they happen out of context. That is where whenever interrupt occurs, you won't have a call. That is a problem. Whenever an interrupt occurs, the same thing should happen. But the problem is, where do I get this new CS and IP? This new CS and IP are stored in somewhere called as interrupt vector table. So what size should be this interrupt vector table? What is this interrupt vector table? This interrupt vector table is a table which stores bunch of addresses. What addresses it will store? It will store CS and IP. So how much storage do I require? Oh, these are 16 bits and these are 16 bits. So total of 32 bits of space. That means I require 4 bytes of space for each and every interrupt. Like this, how many interrupts do you have? We have 256 types of interrupts. So total 1 KB of space starting from 00000 is reserved for the interrupt vector table in your 8086. That is how your interrupt occurs. So what happens when an interrupt occurs? You push your CS, IP flags, you figure out what type of interrupt you are with, and go to the IVT, fetch your new CS, IP, go to the program, execute the program, and then come back. So that means we have a pointer of a pointer. What your table is storing is the addresses. It is as simple as your textbook. So you have a page of contents. Your page of contents is a list of addresses, and the contents will have introduction is available in 54. So that's the address that you are trying to give using a IVT. So IVT can be related to the contents page of your book. So this is the thing with the interrupts. Coming to procedures and macros are nothing but functions. Why do we use functions? When there is a repeated lines of code, whenever we have bunch of lines of code, maybe I want to interpret like this. Move AX, BX, add AL, BL, add BL, so maybe these are the 2 lines I want to repeat, or let us put it more simpler way. I'll write a code in this order: 1 2 3 4 5 3. Okay, every line interprets the unique statement. So what are the things which are getting repeated here? 3 4 is getting repeated. So what do we usually do? You make a function out of it. So how do you make a function? I'll cut this code, I'll wrap it under a name called a function, and whenever required, I'll call this function. So those functions are called as procedures. So how do you write a procedure? We'll write like, you'll wrap this 3 4 inside a procedure and put a return. You'll start with a proc and end with an np, xproc and xnp. How do you call a proc? Your program will be 1 2 call x, 5 call x, 6 call x. That happens to a procedure. That is a regular way how you write a program using a function. And there comes in a macro. Macro is a bit different from procedures. How does it differ? You define a macro on the top. So how do you define? Y macro. And again I'll insert the same. And I'll end with and macro. How do I call a macro? Is 1 2 y, 5 y, 6 y and 7. What is the difference that we see between these is, you are giving a call here and we are calling the value directly. What happens between a procedure and a macro is, in a procedure, whenever you are making a call, the program goes here, executes and comes back. And whenever you are executing a macro, what happens is 3 4 comes and inserted here. So this will be replaced by 3 4. Again this will be replaced by 3 4. This is as good as the original program that we usually. Both have its own advantages and disadvantages. what is happening here, which is more advantageous, we can say both. What is happening here, whenever you are making a call, you have to go there and come back. This is where you have to do lot of pushes and pops. We have to execute more number of lines of code. Here it doesn't happen. That means whenever your code size is large, what do we usually prefer? We usually prefer procedures. But if the repeated lines of code is usually less, maybe these 2 lines, instead of running 3 and a couple of lines, we are making 3 pushes and 3 different pops. Instead of that, we can simply use a macro which will actually replace the code. Where is the code footprint getting? Footprint is the size of the code. Which has more size of code, macros will have the more size of code, because the number of times 3-4 is getting compiled is every time. So 3-4 will have every new address in every set of the program. Here the statements 3 and 4 will generate only one set of address. So the length of code is the executable size will be lesser in procedures, whereas more in macros. Similarly, who will compile faster would always be the macros. So maybe that is why you would have already understood why we don't use functional programming or Python or somewhere when we are writing an operating system, because which involves a lot of functions will consume a lot of context switching times, and that is where we save a lot of time using macros, and most of the times we end up using the procedures as well. It is again depending on the way we want to use. So this will sum up the whole 8086 and the CO1 and CO2 that we are trying to have in the syllabus. So we have covered the 8086 with the programmer's model, architecture and the pin diagram. One thing that you can expect in addition is the programs. So from the instructions you will be either asked about the programs that you have to write from the instructions or from a simple problem statement. The next set of processor that we travel across will be 80286. The best way that you can understand every processor that comes up from now is by comparison. So 8086 have a set of features. So what 8086 has? 8086 is a 16-bit processor. We have a 20-bit address bus and a 16-bit data bus and a bunch of registers and so on. So all these features will be replicated to each and every processor that we are going to discuss. One is 80286. 80286 processor is the next generation of processor which has 4 units compared to 2 different units in 8086. We have BIU and EU, which are in turn divided into bus unit and address unit, which will generate the address part. So what are there here? The physical address generation is done by the segment base and the segment size. And we have the here we have the latches and transceivers, which we have the same in the 8086 configuration. And the important things that we need to know is the 6-byte prefetch queue, where the fetched part will be stored in a 6-byte queue. And the processor extension interface is where you actually can add maybe a math processor or a floating point unit in addition as a co-processor system. So acknowledge and the request, and this is where you go out and get in the address or the data or the instructions. Once you get in all the instructions which are stored in the decoder, and we have a special 3-byte decoding queue where 3 things are pre-decoded earlier before sending into the control unit, and the data obviously will go to the ALU, and the results are stored in the either in the registers or brought back to the memory. The architectures, again, the best way that you can remember or understand the architectures are again with the comparisons. So BIU and EU parts remains the same, but a couple of features get added. And one important thing are the modes. We have 2 different modes. One is a real mode and is a protected virtual mode. Real mode is similar to your 8086. It works same as our 8086. Protected virtual mode is one that we are trying to discuss. Before we go into the protected virtual mode, the set of registers that we have in 80286 are the same as 8086 because it's a 16-bit processor. We have all the same set of registers, and additionally we have one thing called a machine status word, which is an extension of our 16-bit flag. The 80286 came with an additional 16-bit flag, which adds up to be a total of 32 bits, which is prepared for the future generation of processors. We have in the protected mode, we'll discuss more about how we are going to generate the protection part. And the important part here that we have to more focus on is the virtualization. How a virtualization usually works. We have a CPU and we have a main memory. And then we have your secondary memory, which happen to be your hard disk or somewhere. Our programs resides on the secondary memory, but your CPU will execute the programs from the main memory. That means, or your RAM. That means whenever we want to execute a program, your program which is there in the hard disk should come on your RAM, which is to be fetched by the CPU. The problem here is the size of the main memory. Usually in your computers, we have a 4 GB of RAM. I'll summarize the whole virtualization part that we are going to cover in the next couple of things using this example. Maybe I have a 1 GB of RAM. Maybe today I have a 1 TB of hard disk. And all my programs will be of different sizes. How many programs I can store here is maybe summing up to 1 GB. That means if I open a Chrome browser, my Chrome browser application gets onto the main memory and then CPU fetches it. Whenever I open a tab, I create much more space in the main memory. Whenever I open a game, the game contents are actually coming and storing in the main memory. That is where the clear difference that we can find. There is a program of 10 MB, there is a program of 100 MB, and there is a program of 2 GB. If I open a 10 MB program, it has its space in the main memory, it has its full available space in the main memory. But if I open a 100 MB program, maybe yes, it still has a space in the main memory, it can be loaded and it can be run. But if I try to open a 2 GB program, the program should entirely come and store in the RAM, which is not possible because of the physical limitations. So, but CPU doesn't execute until it finds everything in the RAM. So how do I solve this crisis? That is where the virtualization comes in. What does a virtualization do? Virtualization creates a make-believe system where the processor will assume that it has 2 GB of RAM. So how does it usually happen is, if I have a 2 GB of program, I won't have a single block of 2 GB of program. I'll create them into more number of blocks. Maybe 500 MB, 500 MB, 500 MB and 500 MB. Or maybe much more lesser, 100 MB, 100 MB, 100 MB. Like that, I end up having maybe 20 different blocks. So do I have the space for the 2 GB of program? Still no. But do I have the space for 100 MB of program? Yes. So this part of division is what we call segment, or maybe we can still call it paging. So what do I need to do? Your whatever code is being executed will come and stay on the main memory, and rest of the things still stay on your hard disk. But what does virtualization do? Whenever you create a virtualization will allot 2 GB of space in the hard disk, and it will tell that CPU that okay, you have 2 GB of RAM and the whole program is available there for you. Okay, so whenever I want to execute this program, the code that is to be executed will stay on the RAM and rest of the things still stay on the hard disk. Maybe if this part is completed, this will go back and rest of the parts will come in. That is why that is how we are synchronizing the RAM and the hard disk and creating a virtual system where your hard disk is behaving like a RAM. But does it really work as RAM? No way. So, but is the CPU interacting with the hard disk to get the data? No. The CPU is always talking with the RAM to get the data. That is where the role of your memory management unit comes in. the memory management unit brings in the brings in the blocks of code which are required and put it in the main memory, and the rest of the program still stays on your hard disk. And where does the virtual space exist? Virtual space exists always on your secondary storage. So how much RAM does the CPU happens to have is maybe 2 GB. If at all I have 4 such programs of 2 GBs which are running in parallel, 100 blocks, 100 blocks. So a block of this, a block of this and a block of this will come and stay here. And everything maybe are of 2 GB of width. CPU will believe that it will have 6 GB of RAM in a virtual space, but it really still have only 1 GB of RAM. So what virtualization does is, virtualization makes the CPU believe that it has the amount of RAM that it actually needs. So we are dividing the whole memory part into something called segments, and every segment will have a descriptor. So handling all these segments is a very difficult part. So going inside a segment to figure out what that segment does is a difficult part. So what we need to do is, every segment is something coming up with something called as a segment descriptor. And what does it do? It's a header. Maybe if this is a segment, there is a piece of code which is called as a descriptor, and every such segment will have a descriptor. All these descriptors will come and store in a table called as a descriptor table. So this is similar to what we have seen in the interrupt vector table. It is the same as your contents page. We have bunch of, you can still look like chapter 1 and you will have subtopics. So every subtopic happen to be your segment. Every segment will have a different address where it is stored. What is the information that a segment descriptor need to have? Maybe you need to have a starting address, base address, offset address, and maybe a bunch of permissions that we are going to see. So how many kind of such segment descriptors we have are the data, code, system and gate. So gate happens to be all your interrupts, functions, and data is where you store your data. So the data code, the data stack and extra comes under the data segment descriptor. By the nature of the way it works, those 3 falls under this. These 2 are usually for application level, and these 2 are for the system level. So the system level descriptors and the application level descriptors. Application descriptors are local, system level descriptors are global. That is where your local descriptor table and the global descriptor table comes in. That means all the local descriptor tables will have the addresses or the segment descriptors for data and the code segments. All the global descriptor tables will have the system descriptors that happen to be system and gate. This is one thing that we have to remember. So global and local. So with a case study, we'll try to understand how the segment descriptor is defined. Like I said, I have a CPU, I have a RAM, and I have a hard disk. This is where my programs are stored, and this is where my programs are getting executed. And this is where my programs are brought in to get executed. And where does my virtual memory exist? Virtual memory exists in this space. So let us take a simple example of a program. Maybe this is a main program. This is addition, subtraction, multiplication and division. I have how many segments I have created? You have created segment 1, 2, 3, 4 and 5. So main program happens to be a switch program which I want to select plus minus into or a division or some other operation. Let's make an example so simple. Ideally, what do I need to run the whole program onto the RAM? Maybe no. Actually, that is the case. I am wasting up the space in the RAM. So what do I try to do? I'll bring in only the main program. That means the segment descriptor, the segment 1 will be coming onto the RAM, and CPU will interact with the segment 1 and figure out what operation the user wants to do. Let us say I have selected plus. then what should happen? The plus should come onto your RAM. After executing the plus, I'll go back to the main program. Then I have chosen something called minus. So what will happen? The segment minus will come onto the RAM. At this point of time, do I need the plus program to still stay on RAM? Maybe yes, maybe no. Maybe I'll wait for a couple of turns and I'll slowly discard this and put this back onto my hard disk. That is where you are using 5 blocks of segments in a virtual memory, but always there are only 2 blocks which are really available in the physical memory. This way, how many such programs I can accommodate? I can accommodate more number of programs. The process of bringing from the secondary memory to your primary memory is called swapping, and returning back is called as unswapping. So there will be lot of swaps and unswaps that happen throughout the code or throughout the programming, and who will handle this is the role of your MMU. I'm not linearly telling what an MMU does. So MMU does lot of things. So what does MMU does? It takes care of the virtualization, and it takes care of the transfers between your hard disk and your primary memory. It does the swap and unswap. It finds out what is necessary and what is unnecessary. And how do I find this segment is using a descriptor table. And this is a segment descriptor table that we have, and you totally have 8 bytes of segment descriptor. So 1, 2, 3, 4, 5, 6 and 7, 8. Total 8 bytes of segment descriptor. What do you have in the segment descriptor? Like we said, the address, the offset address happens to be a 16 bits. The base address happens to be a 24 bits. That means 80286 has an address bus of 24 bits compared to 20 bits of 8086. And this space is reserved for Intel for the future use. So this is pretty much simple. Drawing the whole segment descriptor part is pretty much simple. And this is the important part of the segment descriptor. And this is where your protection part also comes in. If you look at how this works, I'll explain bit by bit. We'll quickly go through this bit by bit. P will tell whether the segment is present or not. Where is it present? It is 1 if it is present on RAM. If it is 0, it is present on your virtual memory. So what is the status of segment descriptor 1 is P is equal to 1. What is the segment status of 2 is 0. 3 is 1. 4 will be 0, 5 will be 0. So whatever segments are staying on RAM will be treated as 1, which are staying on virtual memory or your hard disk still stays as 0. How it will help me understand is, this will help you understand what segments are being used and what are not being used. Whatever are 0 are still being on the hard disk, which are being unused by the processor. Whenever P becomes 1, that means I can use this and try to execute it. DPL is a descriptor privilege level. So we have 4 privilege levels, 0, 1, 2 and 3, 0 being the highest and 3 being the lowest. This is where your protection part comes in. In the PVAM, P part comes here. If I want to access a higher privilege level, it rejects you. So as a privilege level 3, you can't access 2, 1 and 0. As a privilege level 2, you can't access 1 and a 0. As a privilege level 0, you can access anyone. This happens when you are accessing your system files. You can't delete a system 32 file in your operating system. What does it do? Or whenever you are trying to install a software, it will pop up and ask your password to be entered. So why? Because you don't have the enough privilege level to access this. That is where you end up giving the protection. This is not there in 8086. In 8086, any segment can be accessed by anyone. But in here, there are bunch of segments available, but who can access a segment is who has the higher privilege. So whenever I come across this segment, I'll read the descriptor. Once I fall in this descriptor, I'll decode this P. If it is present, maybe then I can access. Then I'll go into the DPL. I'll compare my DPL. I should either be equal or lesser. If I'm equal or lesser, I can access this descriptor. Otherwise, I'll be thrown out. and then the segment. The segment will select between the LDT and the GDT, whether you want to select the local descriptor table or the global descriptor table. So local descriptor table happens to be the code and the data part. So if at all I select 0, you are selecting the gate and the system. If S is equal to 1, you are selecting the code and the data. That means we have 4 categories. So how do you select between the 4 is based on this. So if it is 0, you will select 2, and if it is 1, if you will be selecting rest of the 2. And then the extension part, E, will tell whether it is executable or not. Who gets executable? Code segment gets executable, and the data segment is not executable. So if it is 1, you are using a code segment. If it is 0, we are using a data segment. So this segment descriptor will tell me, P is telling me whether it is present on RAM or not. DPL is my privilege level. S is telling me whether it is system or system or an application, or a local or a global descriptor. And the next level is telling me, okay, you selected a application descriptor. That means you either have a choice of a code or a data. So where should I select code or data? Yes. If E is equal to 1, it is your code. E is equal to 0, it is your data segment. And code has a executable part, and you can see here, code can either be executable or not, and data can either be expanded or not. Similarly, we have read or write. Read or write is a pretty simple thing. The common thing that we have for an executable program is execute, and in addition we can have either write or not. The same thing happens with the data. Data is by default readable. The privilege that you have to give to me is whether I can write or not. That means if I give the access to your descriptor, that means I gave you the privilege to read when you are talking about a data, to execute whenever you are talking about a code. What is the additional privilege that I can give you? Along with execute, you can also read. What is the additional privilege that I give you for a data segment? You can read by default, you can write additionally. So that is the additional privilege that you can give here. And the last one is the access. Whenever P will tell whether the segment is there in the RAM or not. If the CPU is utilizing the same descriptor, A will be 1, whether it is being accessed or not. So if the A stays 0, that means you can clearly unswap it. If A stays 1, you need to put it on your RAM for continuing the execution. So these are the privilege levels that we have. We have 4 different privilege levels, and in continuation we have 386 processor. From 4 parts we ended up having 6 different parts. Addressing is done by more number of people here. We have a segment unit, we have a paging unit, which is a new part here. Paging is first introduced in 386. We have a bus interface unit which will generate the address and data bus and brings in the data, and we have a prefetch queue, and then we have an instruction queue which will decode, and then the execution unit we have the same, and the barrel shifter is a additional block that we have. So in addition to your regular ALU, we have a shifter separately which is helpful for doing the shifting operations. And then we have a segment unit which will have the segment catch and the segment unit. See, the additional thing that we have here is a paging unit. So paging is one of the mode that we have in 80386. We can either optionally use paging or not. Paging is similar to the descriptors. In turn, we are dividing the whole set of descriptors into something called pages. 80386, in addition to 80286, the features of 386 is it's a 32-bit processor. So your registers are all 32 bits. So instead of AX as a 16 bits, we have EAX, BX, ECX, ESI, EDI, EIP, and E flags. Like I said, we have 3 different modes of operation. One is a real mode, Real mode is same as 8086. How much memory we have? We have only 1 MB of memory. Protected virtual mode is where you have your whole space that you can use. We have 30 bits of address bus that you can use and extend up to 4 GB of RAM. And virtual mode is the third mode. The key part is the address translation. So how do you translate a physical address? Ideally we have a base address, we have an offset address. There is a formula for converting, and we'll end up having a physical address. We used to have that in the segmentation part till now. In addition to that, we in turn divided into something called pages. So we will get a segment address and the base address and the offset, and maybe we can end up having a physical address. This is one way we can generate a physical address. The other case where we can generate a physical address is using paging. When we use paging, we are much more dividing the blocks into something called pages. So we have a base address which will select the segment. From the segment, we need to select a page. In a page, we need to select the address, and then we'll translate it into physical address. So two forms are possible. That means whenever we don't use paging, your segment address, your linear address is equal to the physical address. If we have paging, your linear address is going to the paging, and the page translates into something into your